office. Okay. All right. Only one thing I can think of in way of an announcement. Normally my office hours today would be 11:15 when this class is over with until 3:15 when my next class starts. However, today we have a faculty meeting. Fortunately, it's on this campus right across the way at Ethel Hall building, the auditorium there, and it starts at 2:30. So that means I have to leave the office 2:20, 2:25, something like that, to be there in time for the meeting. So my office hours today are a little bit shorter, 11:15 until about 2:20, 2:25. Then after that, I'm back here teaching, and I'll be teaching until 7:45 tonight. Now, we usually, I think the lab will probably not take quite so long today, so I may be back in the office sometime around 7:15 or something like that. But if y'all are still around, you're welcome to come see me if I'm back. Good deal. Any questions? All right. Now, just a tad concerned on a couple of issues here. Number one, research papers, I've gotten, one. Yeah, okay, only one. Okay, those should be coming in. We're in the last month of bonus and basically almost the last month of the term. So please, folks, get those in. Test one, I think all of you have turned them in, but I'm still missing 3. That's why I can't return them to you. So hopefully those will be coming in. And test two, none. Okay, have been turned in. And I just gave you test 3. Did you get a copy? Okay. Now, you look awfully cold, are you? Okay. This is the warmest room that I have found in the building. So if it's a bit too cold, it may be because of the window. Okay. All right. So you need test 3. Here we go. Okay. Now, can't think of any other things that need to be addressed housekeeping-wise. Okay, where we left off last time, we just had gotten started in 6.1. Just barely got maybe 1 or 2 slides done. Okay, what we're talking about in 6.1 are oblique triangles, which are not right triangles. Okay, meaning that the biggest angle is either less than 90 or greater than 90, but not 90. Okay. Now, that's triangles with no right angles. Now, when we're drawing these triangles, since none of them are a right angle, none of the sides are any more special than the other sides, the standard notation is just number or name the 3 vertices, the angles, capital A, capital B, and capital C. Okay? Now, with those in place, then the side opposite angle A will always be length little a. The side opposite angle B will be length little b. The side opposite angle C will be length little c. Now, can anyone tell me anything about the relative lengths of those angles? I mean, lengths of the sides as compared to the measure of the angles. You've never noticed it before. Let me give you a hint. Okay. Which of those 3 angles appears to be the smallest angle? A, B, or C? B does. It looks like it's the smallest. Guess which is the shortest side? B. Little b. Okay. Always the smallest angle, the side opposite will be the smallest side. And along with that, I can't tell for sure, but I think maybe angle A is larger than C. The side opposite the largest angle is going to be the longest side. And of course, the side opposite the middle angle will be the middle side, just like in whatever the nursery rhyme is. Never mind. Okay. So to solve an oblique triangle, that's what we call it, to solve an oblique triangle, we need to know three pieces of information. Okay? And then to solve it, we need to calculate the other three pieces of information. We have 6 pieces of information, 3 angles, 3 sides. Okay? So to solve an oblique triangle, you need to know the measure of at least one side. You cannot solve a triangle if you don't know any sides. You've got to have at least one side. Okay? Then, after that, you can either have one angle and another side or 2 angles. Okay? You need 3 pieces of information, at least one side and any 2 other measures, either 2 sides, 2 angles, or an angle and a side. One of those 3, but you've got to have at least one side. Okay. Now, this breaks down into 4 cases. Okay? Actually, it kind of is like 5 cases, but we linked 2 of them together. If you know one side and 2 angles, any 2 angles, that could be the angle side, or angle side angle. You just know 2 angles and one side. That's one of the 2 cases in it. You can solve that triangle every time. No sweat. Well, maybe a little sweat. Now, if you have 2 sides and an angle opposite one of them, okay, you have to have the angle opposite one of them. So it's side-side angle. And we always say side-side angle. We never say angle side-side. Okay? Never mind. Okay. Now, if you do that, now here's the key. You may be able to solve that. There are some cases where you won't be able to solve if you got 2 sides and an angle. They're just not solvable. Okay. If you have any 3 sides, if you have the 3 sides, you can always solve that. Not in this section, though. That's going to be law of cosines. Now, if you have 2 sides and they're included angle, and that's why the angle goes in between the sides, you can solve that too, but not in this section. These 2 will be in the law of cosines. Only the first 2, sort of 3, will be in the law of sines. Okay? So we'll do law of sines for these 2, and the next section will do law of cosines for those 2. Okay. And even when we're doing law of cosines, sometimes you'll come back and use law of sines. So you may use it again, but you're definitely going to use it now. So here's what the law of sines says. Let's just take any old oblique triangle here, meaning none of these angles are 90. This is an acute. The largest angle is acute. Here the largest angle is obtuse. Okay? So, here's a couple things to note. You should know already, okay, from a right angle tree. Let's imagine from this acute angle A here, let's drop a perpendicular down from C to the baseline AB. Okay? Now, we know already that the sine of A is the opposite side of this right triangle here, opposite side H over the hypotenuse B, right? So you know the sine of A is H over B. Okay? Now, another way of saying that, if you multiply both sides by B, then you have H is equal to B sine A, right? If sine of A is H over B, multiply both sides by B, and you get B times the sine of A is equal to H. All right. Now let's go over to angle B. And in angle B, there's another right triangle. And you know the sine of angle B is H over A. Because that's kind of your hypotenuse of that right triangle, right? So you could rewrite that as H is equal to A sine B. Right? Here we had H is equal to B sine A. Well, if H is equal to, where is it? Okay. And that's the same H, by the way, folks, isn't it? Absolutely the same H. Okay? So if you have H equal B sine A, and H is equal to little a times the sine of capital B, then that implies that B sine A, is equal to A sine B. Right? Hello. And what I'm going to do here to match up what they're doing, divide both sides by sine A, and that wipes these out, but also divide both sides by sine B, and that wipes those out. Okay? And what do we have? A over sine A is equal to B over sine B. Okay? That's 2/3 of the law of sines right there. Okay? Now what we can also do is drop a perpendicular from angle A to the baseline down here. I'm just going to assume those are right angles, okay? And then what you have is the sine of C times, okay, picture this now. Here's angle C. The sine of angle C is H over B, so B times sine C is equal to H. And if you come over to angle B, the sine of angle B is equal to H over C, so C times sine of B is also equal to H. Now these are different H's, they're not the same H's, but these are the same as each other. Maybe I could have called this H1s, okay? And if these two are equal, that means, where to write? B sine C is equal to C sine B, okay? And again, divide both sides by sine B, and divide both sides by sine C, okay? These go out here, these go out there, and you have B over sine B, which is the same thing we had before, is equal to C over sine C. So there completes our law of sines. Okay? That the ratio of the length of a side to the sine of the angle opposite of that side is constant in every oblique triangle. Even if it's an obtuse triangle. Because if you go down here, the sine of this obtuse angle here is the same as the sine of this is reference angle here. Because sine is positive in the first and second quadrant. So that's the same as the sine here. Well, the sine of this is H over B. And you go back and do the whole thing again. Sine of this is H over A. Same thing is true. And then you drop another perpendicular anywhere for a different H, and you got the ratios always being the same. Okay. Now, can I erase my chicken scratch? We showed that. I also want to, don't have to say it. Okay. I was going to write it down, but I realized they've written it here. You could also write that as sine A over A is equal to sine B over B, which is equal to sine C over C. Doesn't matter which order you write, okay? But keep them all the same. If you have the links on top and the signs on the bottom, keep the links on top and signs on the bottom. If you have the signs on top and the links on the bottom, keep them that way when you're setting up the ratios. And those ratios are equal, meaning you can form a proportion. And frankly, that's going to give you just about all the information you need. Okay? So, when does law of sines work? Remember we have to have three pieces of information. One length, and then one either side angle, length and angles, another side and an angle. Two angles or two sides. Okay? For the law of sines to work, you have to know one side and the opposite angle. If you have that, you can do the law of sines. Okay? Remember the ones you can't do? If you did this side, that side, and the angle in between, you can't do it. Law of sines will not work for that. Okay? Law of sines will not work if all you have is the three sides. It won't work. Okay? But if you have a side and an opposite angle, it will always work. Now, some triangles may not work, but if they have solutions, the law of sines can be used. And it's a really simple formula. Okay? So, here's example 1. For this triangle, and this is also example 1 in your text, okay? For this triangle, angle C is 102 degrees. Make sure it's the same one. Yes. Angle B is 29 degrees and side B is 28 feet. Find the remaining angles in the side. In other words, solve the rest of the triangle. Okay? What's your easy first step? You don't have to anymore. It's already done for you. You can just use the results of that, which is law of sines. You don't have to draw the perpendiculars. But there's something that's really easy to do here. Never pass up on this when it's a gimme like this. If you know two angles of a triangle, guess what? You also know, you know the third angle, so don't pass that up. That's a gift horse, right? So these two add to be 131. And what do you do with that? Subtract it from 180, and that gives you 49. This indicates it would be 49 degrees. Now, you can't always trust the triangles, okay? You can't guarantee they've drawn them properly. But, I think you're pretty clear, this is the smallest angle, that's the largest angle. Anything even close to 90 degrees is usually going to be the largest angle, okay? Usually, okay? That means this angle sure looks like it would be in between those two. Okay? So now relative sizes, that had better be the shortest side. That would better be the longest side, and this should be the middle side. Okay, so you already got one piece already. Find the remaining angle and side, you got the remaining angle done. Now, we got to use something to get the remaining sides. Two sides missing. What do you think will work? Anybody? Anybody? What's the title of this section? Law of sines. Yeah, let's see if that might work. What is required for the law of sines for you to be able to use it? Okay, yeah, well, that's true, but what has to be true about one of the angles and one of the sides? Or the side? They have to be opposite each other. Does this fit the bill? Yes, we do know B and angle B. So we can do law of sines. Okay? How does it run? How does that go? 28 over sine of 29 stomach is growling like crazy. I hope it didn't pick up on the microphone. Okay, I've got one ratio. I need another to make a proportion.
Equal to, we do 102 over, C over 102.
Okay. I believe what you meant to say was C over sine of 102. Okay, the angles are always, take the sine of it, the sides go. So to do a proportion, you got to know 3 of the 4 pieces, okay? One pair we know, and then one other piece that we knew, actually 2 others. And here's J. I don't know if I ought to say this with him not here, or if I should wait till he's here. I'm going to go on and say it now. You know Walter, who sits back there? Walter Carr? You know he's sort of a celebrity. Did you know that? You did. I didn't know that. I mean, I had heard the name Carr, but I didn't know the first name. He made national news. Yes.
I literally saw it on Facebook.
Yeah.
I had no idea that was him.
I didn't either until yesterday.
He said the only thing different is because he dyed his hair. I know pictures to the face.
I know. As they said last week, he was on, was it Steve Harvey show or one of those shows? I don't know if I should have said that or not, but I just found out that was him. I knew the last name was Carr. I didn't even make a connection. I just assumed he wasn't here anymore because this happened, what, last spring or sometime, didn't it? Yeah. So anyway, so you're going to sit in this seat, huh? You're going to get special. Okay. All right. So where do we go from here? We've got our proportion set up. How do we solve that? This is example 1 on page 401. How do we solve that?
You want to get the C by itself.
Okay.
So you multiply the sine of 102.
Okay. The technique is called cross multiplication, right? Multiply the product of those two, right? This is if it's across an equal sign. So I'm going to write out the first step. Sine of 29 degrees, C times the sine of 29 degrees is equal to 28 times the sine of 102 degrees. Okay? And then to get C by itself, we'll divide both sides by sine of 29 degrees. Okay. So these go out. So C is equal to that quotient. If you got a good calculator, it'll work. It should work. 28 times the sine of 102 divided by the sine of 29. On the calculator, punch that in and see what you get. Now, if you get a number less than 28, we've made a mistake. Right?
56.
Second?
56.49.
Okay, I'm going to round that to just 56. And that's just me being picky because as a physicist, scientist type person, if you only have two significant digits here, 3 there, 2 there, you can't get more than 2 in your answer. There's 2 there, there's 2 there. That's why I rounded it to 2. The book is going to give it to something like you said, not 4 digits. You don't have 4 digits of precision, you can't do it. Okay, now what? We've got angle A, we've got side C. What are we missing? Side A. And frankly, there's no easy way to do it except law of sides. Okay? I thought maybe someone might say Pythagorean theorem. No, won't work. Why? Not a right triangle. That only works for right triangles, so don't even try it. Okay? In fact, when we get to the law of cosines, you'll see that looks very similar, but not quite. So how would you set up to do A?
Little a over sine 59 degrees.
Sine what? What did you say? I couldn't hear.
Sine 59 degrees.
Did you say 59? 49. Okay. That's what I couldn't hear. Okay. Is equal to what?
56 over sine 102 degrees.
Okay. Now that is okay. But here's my little rule. Nothing says you can't do that. But I like to always use the thing we know. What if we had made a mistake here? Then that mistake is going to carry and make this a mistake. So since this was the thing I know, I always like to use the ratio I know is absolutely correct. Now, an extension of that is the fact we did round this one off, remember? So then you're propagating your round-off error. Okay? Then I would use as many digits as I had there, but to keep from using all those digits, use the ratio you know. That's my little thing. It should work. It should work perfectly fine the other way, but just in case you did make a mistake or copied something down wrong, this is now 28 over sine 29. Okay. And by the way, I've got an apology to make. We've been talking about you. Yeah, I think you probably know why. I didn't realize until yesterday you were the man. Okay. And so I just told the others. Yeah. So congratulations, you do us proud, even though we had nothing to do with it. So thanks for putting us on the map. Okay. Okay. All right. Where do we go from here? We've set up this ratio. We're doing example 1, top of page 401. Where do we go from here? Okay. What does that give us?
28 sine 49.
Okay, 28 times the sine of 49 degrees
Equal to a times the sine of
24 degrees, and then we can divide both sides by sine of 24 degrees to isolate the A. Okay, these go away. So you get A to B.
Where'd you get 24?
I'm sorry? Oh, I can't read my own writing. Oh, I can. Where is that?
Sine of 29.
That's okay. That's partly not being able to read my own writing, but then the other part, I've got all 24s. No, yeah, that's right. Yeah, that's it. That's the 29 degrees. You're right. I can't read. Okay. So, yeah. What is A? Let's round that to 47 feet. I'll put approximately equal to. So C we had approximately equal to 56 feet and A approximately equal to 47 feet. Okay. Now, our earlier observation was that we expected this to be the longer side because it's not the biggest angle. Sure enough, it is. We expect this to be the shorter side because it's not the smallest angle. Sure it middle one is just right. Okay. That's how we figured. Like I say, they're going to give a lot more decimal points than I am. Frankly, I don't think those can be justified. Because if you only have 2 digits going in, you can't get more than 2 digits coming out. Okay? But let's see what they do. Let me erase all mine. Wait a minute. Did you say 47?
No, I said 43.5.
Oh, I can't hear. Okay. So let's make that 44. Okay. Approximately 44 feet. Okay. And the other was 56. Close to 56 feet. Really close to 56.5 feet, but we'll leave it at 56. All right, now I can erase those. All right. Like I said, the easy thing to do, if you know 2 sides of 2 angles in a triangle, you know the 3rd angle. So go on and get that done first. And that's what they did too. And that gave them 49 degrees. Exactly what we got. And that's exact number, 2 digits, exactly right. No question there. All right. Then after that, you can use the law of sines. Now in this problem, we knew B and sine B, so that's the pair we're going to use. We get A from that. And that's how they set theirs up, and it's perfectly fine. I don't want to have to memorize that. I like to use my proportion, the way y'all were doing it too. But actually, I'll show you the way I really do it. Since we knew this one, and this one, to get A is sort of using this. Your numerator is always going to be the product that you know, B sine A, divided by the part that you don't know, that's part of this, sine B. So you can, just from your law of sines, you can write down what A is, which is exactly what this is, B sine A divided by sine B. They write the ratio B over sine B that you know times the sine of the angle that you know as well. Any way you want to do it works, okay? So let me back off. Well, as long as you do it right. Sorry. Wrong. Okay. Get my pen back. Okay. So now you just plug in 28 over sine 29 times sine 49. Exactly like you did. And they get 43.59 feet. Where do they get 4 digits of precision? Nowhere. That should be rounded to 44, I think. Okay. Then, also using law of sines, you get to C. The other side you don't know is B over sine B, the ratio you know times sine of C, which you also know. That'll be your 8 over sine 29, 28 over sine 29 times sine 102. Or the way we did 28 sine 102 divided by sine 29. However, and that comes out close to, just really close to 56.5 feet, but we only have precision for 2 digits. So I would say round that to 56. Close enough. Okay. They are going to jump to an ambiguous case, but let us do example 2 before we get to the ambiguous case. A pole tilts toward the sun, and this is bizarre, but this is what they're doing. It doesn't always tilt toward the sun. The pole's fixed in place, the sun moves. But at this moment, the pole is tilting toward the sun at an 8-degree angle from vertical. So if here's the sun up here shining brightly, okay, here's a pole here that's tilting just ever so slightly toward the sun, and that ever so slightly is 8 degrees. Okay. and it casts a 22-foot shadow, meaning the sun over there, so the shadow here is 22 feet. Okay? That should be horizontal, and mine isn't. Okay? The angle of elevation from the tip of the shadow to the top of the pole, so you're standing down here and you're doing this angle of elevation here is 43 degrees. All right, here's Jalen. We got 5 out of 9. Okay, so we're over 50%. All right, we're example 2, bottom of page 401. Okay. All right, I think that's all they give us here. The angle of, yeah, okay, we got that, 43 degrees. The question is, what is the height of the pole? That's what we're looking for. We got a pole that's tilted toward the sun. The reason for that is it's casting a shadow, and that should be perfect. Okay, shadow should be horizontal. Mine isn't. You get the idea. The pole is tilting 8 degrees from vertical. The angle from the tip of the shadow to the top of the pole is 43 degrees. The shadow has length 22 feet. Now, whether any of my drawing is reasonable, hard to say. 8 degrees is probably not too close. 43 doesn't look too bad. 22, I don't know how it should compare to the height of the pole. I just drew it. Okay. So that's what we're looking for, height of the pole. What other bit of information can we use?
Do you find that the angle where the pole is at, because you have 8 degrees and then you know that there's a right triangle, there's a 90-degree angle from the line, so it would be 98 degrees.
Okay. I heard something about a 90-degree angle, and what was the other part?
And then the other side's 8 degrees, so that would be 98 degrees.
Got it. So this angle down here, the big angle here, is 98 degrees. You want to give it a name? Does it matter to you?
Well, the picture says it's B.
Oh, it does say it's B. I would have called it C, but yep, they called it B. So B is equal to 98 degrees. All right. Now, what do we need for a law of sines to work?
Either 2 angles and the angle and its opposite.
Yes, and we have 2 angles, but we don't know beans about the opposite side. What we're looking for is opposite 43 degrees, so that's going to be useful for the unknown, but we don't know anything about the opposite side from 98, do we? So are we sunk?
We can find out the opposite angle.
Yes, we can always, if you know 2 angles, you always know the third. And what is that? Okay, 180 degrees minus 141, isn't it?
Yeah, this means 39.
39. Okay, is that what you said? Okay, I thought you said 89. I thought, oh, 39 degrees. All right, so this angle up here is 39 degrees. Okay. Yep. Okay. Now we're ready to cook, right? Now we know an angle and the opposite side, so we can use law of sines. What is the side we're interested in? Okay, if you name this A and this little a, that's what we're interested in. Who cares what that long side is? There's no importance in the problem at all to that side. So don't even use that 98. Let's just use the 2 we know. Okay? So, how do we use law of sines here? 22 over sine 39 equals little a over sine 43 degrees. Do the math. What you get? What's your setup?
The
22 times the sine of 43 degrees over the sine of 39 degrees. Okay? And what would that give us?
And then
0.84? Okay, so let's call that 24 degrees. Okay. No. 24 feet. Don't get the units messed up. 24 feet. Okay. Does that look like it makes sense? This angle is just slightly more than that one, right? So it would make sense that this side would be slightly more than this one. It is. Okay? So at least that looks like it makes sense. 24-foot pole. That's out of the ground pole. They say 23.84 feet. Yeah, right. Let's round that to 24. You just don't have the precision to do otherwise. Okay, there is a checkpoint at the bottom of that page. Please do that as soon as you can after we get out of class. All right, now we're ready for the ambiguous case. Yeah, we just had gotten started. Now you got to get ambiguous on this. This is always will come in the form side-side angle. And again, never say angle side-side. Okay, but side-side angle. Example 1, we saw we had two angles in one side. Example 2, we had enough information to get two angles and one side. However, if two sides and one opposite angle are given, you may have one of three situations occurring. Either there's no such triangle, okay? Or one such triangle does exist, or two distinct triangles may satisfy all those conditions. If anything sounds ambiguous to me, that surely does, okay? You may have no solution, one solution, or two distinctly different solutions. I mean, meaning two completely different triangles that you have to satisfy. Okay. Now, they're going to do a table here, and while this is all true, it's really awkward, okay? And I seldom go back, except when they do, and check it out. So we're going back to this concept of our H there, that perpendicular line there that's the height of the triangle. So here you're given two sides, but one angle that's outside the two sides. That's why it's side-side angle, okay? Not the angle between the two sides. Now, here's the deal in general. This won't always help you perfectly, but it will be general. Now, you got two possibilities of this angle here. Either it's an acute angle or it's an obtuse angle. We'll deal with the four possibilities with it being acute first, and then we'll deal with the two possibilities with it being obtuse. Okay. If A is a relatively large angle, okay, relatively large angle, then the side A they give you is relatively small, it's probably never going to work. Because if B is considerably larger than A, and A is a pretty good sized angle, there's no way A is ever going to touch the ground. It could, barely, but most of the time it's not. So if A is acute and A is less than that ratio, you know, remember we had sine of A is equal to H over B. So H is equal to B sine A. If H is less than B, if A is less than B sine A, it's never going to touch the ground. Okay? It won't reach the baseline. It can't reach the baseline. If A is a big angle but little a is a short side, it may not work. Now, if it's exactly equal to H, again, I wouldn't even bring in the H. I would just use B sine A. That's what H is, so B sine A. B sine A is equal to B sine capital A is equal to little a. Then you have exactly one triangle, and it's a right triangle. You don't need long sines anyway. Okay? But that is a single triangle. Okay. But if A is greater than B sine A, or in other words, if A is ever greater than B period, then it's going to be fun. That will always result in an A. If A is greater than B, you're always going to have a triangle. Okay? If A is less than B, then you have to test. If A is less than B sine A, you won't have an A triangle. If A is equal to B sine A, you will have a right triangle. Okay. Here's where the trouble lies. What if A is less than B, but H is less than A? In other words, your B sine A is less than A. That means that you either are going to have A could be swung out here, or A could swing in here. So this would then produce an obtuse triangle, or this one would be another acute triangle. So that is really the ambiguous case. You could have two different angles that fit those same conditions perfectly fine. Now, let's go to our obtuse angle. A is an obtuse angle. Okay? Guess what? This can't happen then because this requires this angle here to be greater than A. And if A is obtuse, there's no way it will be for a triangle. So we're down to just two cases. And again, if A is less than B, okay, don't worry with H's at all here. If A is less than B in this case, this is an obtuse triangle. You can't have it because if that's an obtuse triangle angle there, A's got to be your longest side, right? Got to be the longest side. If B is greater than A, it's not your longest side. It's never going to work. Okay? But if angle A is obtuse and the A is greater than B, then they'll always work. Okay. So if A is greater than B, it always works. Always works, no matter if it's obtuse or acute, angle A. Okay, if A is greater than B, it's always going to work. It's when A is less than B, if it's less than B sine A, it'll never work. If it's equal to B sine A, it will be a right triangle. And if it's something in between B sine A and B, you're going to have two solutions. And that's really ambiguous. A is greater than B. That's the one we look for and hope for. Okay. These are with the side-side angle. I never go back and work those. I just see what happens. Okay. Now, here's example 3. Okay. And you can go to larsonprecalculus.com for an interactive version of this type of an example. So here's what we got here, folks. Now, if you can see the triangle, if they've drawn it for you and drawn it correctly, it's going to have a solution, right? No way around that. It's there. So here we know that little a is 22 inches. Little b is 12 inches, and the angle here is 42 degrees. Well, guess what? We know this is going to work because A is greater than B. It's got to work. No question about it. There will only be one solution. There can't be any more. Okay? So, pretty easy to do. It says find the remaining side and the other two angles. What you want to go for first? I don't care, really. Well, I do too. Not much. Yeah, I do care. There's only one possible thing to go for. What's that? You tell me. Or in other words, identify your things you know. The pair that you know. A and sine A. Okay? You're going to use law of sines, so that's going to be 22 over the sine of 42. It's got to be. Okay? Now, here's why I said there's only one way to go with this. You've got to know one of the other two things. And there's only one of those that you know. What's that? Yes. Is equal to 12 over the sine of capital B. Okay? So now we're going to have to figure out what B is from that. So where would you go from there? Okay, and what does that give us? Okay, 12 times the sine of 42 degrees, I'll buy that, is equal to 22 times the sine of B. Got it. And now what? Now what? Help me, somebody. What are you wanting to? Okay. Yeah, get sine B by itself. So divide by 22. Okay. So sine B is equal to 12 times the sine of 42 degrees over 22. Place that in and see what you get. What kind of number? Second? 0.364. Does that seem reasonable? Why? Exactly. And in fact, even more reasonable than that is between 0 and 1. If that was between -1 and 0, that meant you would have to be in the third or fourth quadrant. Can't be. Okay, you can't be. Okay, so that would not be possible. So we want it to be positive, in fact, and it is. Okay, how do we find out what angle B is?
You find the arc sine of.
Exactly. You take the inverse sine of the 0.364, whatever's on your calculator screen. Just do an inverse sine of that, and that gives you B to B, and be in degree mode because this was in degrees. Okay, let's just leave it 21 degrees. I agree the book probably says a 0.4, but look, if this is only 2 digits here, that's only 2 digits, that's only 2 digits. We can't legitimately get more than 2 digits out of this. This is 0.4, we'll leave it at 21 degrees. So there's B. Okay, now by our picture, does that look like it makes sense? Yeah. We know it's got to be less than 42 because A is greater than 12. So, I mean, it's B. So yeah, it needs to be less, and it surely Yeah, that doesn't guarantee it's right, but at least it's in the right ballpark. Okay. As Jacob liked to keep it in the ballpark. No, you want to get out of the ballpark. Okay. Next, are you a pitcher? No, you're a... Huh? Outfield. Right. You want to keep it in the ballpark if they're hit. Right. And he'll catch it if it's in the ballpark. Guaranteed. Okay. All right. Okay, we got, actually that was the easy thing. Because what's left, we don't have either little c or big C. Or do we?
Well, we do now. We know the big C now.
Yeah, as soon as we get the second angle, you know the third angle. And what would it be? What would be your third angle? C. Yeah, I got it. Anybody? 117 degrees. Perfect. Okay. Now that you have that, what can you do?
Find little c.
Okay, and how would you do that? Okay, 22 over sine of 42 degrees is equal to little c over sine of 117 degrees. Okay, and how would you go from there? Anybody?
BC is equal to 22 times sine of 117 divided by sine of 42.
Got it?
Equal 29.
It's what?
Approximately
29 inches. Okay? Okay, let's see if that makes sense. Obviously, C is your largest angle. It's obtuse. Can't be any bigger, okay? So little c, it better be your longest side, and indeed it is. Longer than A, longer than B by a large shot. So that doesn't tell you you're right, but at least it gets you feeling like you're in the right ranges, okay? And what did they get? Yeah, it's example 3. 29 inches, yes. And 21 degrees, yes. And somewhere here, I see they have sine of 117 or 16.59, 117 degrees. Oh, there it is, okay. Yeah, 117 degrees. All right. So we have solved that. Sorry. Now, let's see how they do it. I think I can just go to the next slide because that's where it's going to be. By the law of sines, you have sine B, and they like to put the sines on top. I don't know why. Sine B over B is equal to sine A over A. Works the same way. That they call this a reciprocal form, which then would be sine B is equal to sine A over A times little b, or little b times sine A over A. Plugging that in, 12 times sine 42 over 22, which is exactly what we had. That gave us B is approximately 21.41, which we called 21. Then you can determine the side angle C to be about is 180 minus 42 minus 21, which we got to be 117 degrees. Okay, they have digits that they can't justify. Now you go back and again, what my suggestion is all, this is the one we're looking for, and that was the calculator, and we can't get around that. This is the one that gave us to begin with, I hope. Is it? Yes, 22 is out 42 times the sine of, we called it 117. They got the remaining side then being about 29 inches. They say 29.40. 29 is about all you can legitimately list there. Okay. That was example 3. And then what they do is skip the 2 ambiguous cases, which are the ones that are the hardest and the ones that you need to focus on the most. Okay, so let's go back and do example 4. This one isn't exactly ambiguous, but it's, well, they tell you what it is, but they should just let you do it. Here we have A is equal to 15 feet, B is equal to 25 feet, and angle A is 85 degrees. All right. Now, you can start cranking away if you like. They didn't give you a picture, which usually is suspicious. You can start cranking away, and you'll soon see there is no solution. Okay? We'll get to that in a minute. But before you start cranking away, let's just take a look at this. The angle A is 85 degrees. That's awfully close to 90 degrees. So this is going to be, if it's not going to be your biggest angle, it's going to be awfully close to the biggest angle. Even if your one angle is only 1 degree, then the other angle would be 94, right? So, hey, if that were the case, 94 and 85, I don't think A and B could be that far apart. They would be very close to the same way. Okay? They're not. B is way bigger than A, but A is very close to being your biggest angle. How could it be that far apart? So you can almost look at this and say, no, I don't think that was going to work. But without that ambiguity, let's actually do it. Which law of sines work here if it works? That's a weird way to state it. Do we have enough information for it? Yeah, what would you do?
15
over sine B. Okay, and we want to solve that for sine B, right? What would that be? What was sine BB? Sine BB. Huh?
1.66.
Oh, you already calculated it. Say again, 1.66? All right, that makes you feel good, warm, and fuzzy, right?
This doesn't exist, right?
Can't exist. Why not?
It's greater than 1.
Exactly. Sine could never be outside plus or minus 1. Okay? So that's indication. Yeah, our first thought on that, B is way too big, way bigger than A. Doesn't look like that could possibly work. It can. That would require sine B to be an impossible angle. Can't happen. So that is what gives it away. No solution. No solution. Okay? The numbers will tell you that. Okay. Now, example 5, on the other hand, they sort of give it away here. They say A is equal to 12 meters, B is equal to 31 meters, and angle A is equal to 20.50 degrees. Now this you can have a lot more precision in, kinda. I forgot to say there was a checkpoint after the last one. Right after every example, there's a checkpoint. This one they've given you A being a small angle, very acute angle. Okay, so A can be a lot smaller than B. Okay, so there's nothing here saying this won't work. Okay, or even hinting that it won't work. What we have is something that, and if you went back and did the ratios they talked about before, you would see this has to be the ambiguous case. Could have two solutions. Well, let's start with what we know. Let's draw a baseline here. Now, this baseline we don't have any clue about. They haven't told us anything about that baseline. They have told you about this angle here. This is angle 20.50 degrees. So that's a pretty small angle. Okay, that's angle A. Okay. Side A over here is 12 meters. And the thing is, it could actually be doing this and still be 12 meters. Okay. B up here is your 31 meters. Okay. Considerably longer than A. And just the way I've drawn it indicates, yeah, there could be two solutions. In fact, indeed, there are two solutions. If that A had been 3 meters, probably no solution. Not going to reach anywhere there. But this looks like it could, and indeed it does. All right. Where do we begin? Okay, so 12 over the sine of 20.50 degrees. Okay. Sorry about that. 31 over what? Sine B. Okay. We need to identify, we have two possible B's here. We don't know that for sure, 31 over sine B. All right. Let's just let the numbers take us and see what they tell us. Okay? We're looking for sine B again, right? And what is sine B? (31 times the sine of 20.50 degrees over 12. Okay. And what B do you get? Okay, sine B is 0.904. Okay, doesn't matter. Okay, so what possible values could you have for B? What's that?
I got 64.783.
Okay. I think, yeah, 0.78 degrees. Is that what you said?
Yeah.
I rounded. Okay. 0.78 degrees. Probably had another angle with 4 digits. All right. Now here's the deal. That is one angle whose sine is B. That would be your first quadrant angle. But you see you have another quadrant angle over here, the fourth quadrant, where B could be obtuse. I mean, not fourth quadrant, second quadrant, where B could be obtuse. Tell me we're almost out of time. Man, how does that happen? It just seems like it disappears. Okay, we're going to have to finish this one next time. Sorry about that. Unbelievable. Okay, so we'll start back on the two-solution case next time. Let me give you a few homework exercises to do, because I know you don't want to go home a whole weekend with nothing to work on. So I think you can do either 5 or 7. They're both at calcchat.com. Then do any of the odds 9 through 21. They're all at CalcChat. 11's at CalcView. Do any of the ones 23 to 31. They're all at CalcChat. 29's at CalcView. And then do try either 33 or 35 or both. They're both at CalcChat. 33's at CalcView. We'll pick up the rest of those later.
Could you help me with